If we talk about the difference between IP-FRR and Ti-LFA, let's say the primary path from P1 to P7 goes via P3, P5, and then IP-FRR path goes via the P6, that is via the suboptimal paths. So if you remember the calculation, how exactly it figure out, the distance between next stop and destination, in this case it is 100, should be less than distance from next stop to source plus distance from source to destination. This is 3. So yes, in the case of P6 this condition is valid, but you might be thinking why you didn't choose the P4 as a backup path. So let's calculate and let's see why you didn't choose the P4 as a backup path. The distance between next stop to source, this is 3 plus 1, that is 4, should be less than distance from next stop to source, this is 1, plus distance between source to destination, this is 3. This condition is invalid here. This become kind of ECMP scenario, but it should be this value always should be less than this value. Thus the reason P4 is not the best alternate path for the IP-FRR in this diagram. So that is the one of the challenges with the IP-FRR, that most of the time you get the suboptimal paths for the backup path. This is the post convergence path. And then if we talk about the Ti-LFA, it always considers the post convergence path as a backup path. Let's see in the subsequent slides how exactly it calculates those stuff. Before deep dive into Ti-LFA, let's compare the coverage difference between LFA, remote LFA and Ti-LFA. So here I have increased the matrix so that all the prefixes should go via this path which we are trying to protect. So all this R4, R2, R5, R6 and R3 is going via this path. So we should get the coverage for all the prefixes. Let's see how the coverages are. This first is for the loop free alternate, per prefix loop free alternate. Here we are getting the 93.75%. If we go further, if we implement the remote LFA, we get the 100% here. And this is the case for the Ti-LFA. In the case of Ti-LFA, we always get the 100%. As I talked earlier that Ti-LFA is the extension of the loop-free alternate. That's the reason if you check the show ISIS fast reroute and then I'm matching this backup path, so it's just saying that all path has loop-free alternate. You might be getting confused here, but let's cover that into the subsequent slide, how exactly it calculates the Ti-LFA backup path. So as I said that Ti-LFA is the extension of the loop-free alternate, and to enable Ti-LFA we need to first enable the per prefix loop-free alternate, and then second command is for the Ti-LFA. So let's say we remove the per prefix the loop-free alternate command from the configuration. So in that case your Ti-LFA won't work. So you can see here percentage coverage is 0. So to implement Ti-LFA you must have the per prefix loop-free alternate enabled. The benefit of Ti-LFA is that it is completely local operation to the node, and it always provides the 100% protection, and we can have the link node or SRLG protection based on the requirement. It always gives the backup path as a post convergence path. We don't have challenge here like what we have with the IP-FRR, where most of the time you get the backup path via the suboptimal paths, and it can protect the non-segment routing traffic like LDP and IP. So while providing those coverages, we can have no extra segment, we can have one segment, and max to max means most of the time we get two, but where very rarely you will see the Ti-LFA level on the backup path are crossing more than two. It's very rarely, and it's a very so while calculating those backup path via the post convergence path, router figure out the P node, and to reach that P node it use the prefix-sid. It calculates the PQ node. To reach that PQ node it calculates the prefix-sid. It uses the prefix-sid, and to reach Q node it uses the adjacency-sid. We will see in the examples, coming examples, how exactly to use those prefixes and adjacency-sid. So once we configure the Ti-LFA on the node, so let's see we have configured Ti-LFA for this particular interface and we are protecting that. So this debug is running on the PE1. So first it will start with the per prefix loop free alternate. And in this case, it has selected the P2 as a backup path for loop free alternate. So let's calculate again how it is. So distance from next stop to destination, it is 1 plus 1. So by default, metric is 1 on all the interfaces. 1 plus 1, 2 should be less than distance from next stop to source, that is 4, plus distance from source to destination, this is 3. So yes, this condition is valid here. So why not for P4? Let's see. So distance from next stop to P4 to destination, it is 3 plus 1, 4, should be less than distance from next stop to source, this is 1, plus distance from source to destination, this is 3. So this condition is not valid in the case of P4. Hence, you can see the per prefix backup path is going via the PE2. Then now it runs the RLFA. Now it's run the RASPF for the node P3, but it rejects that at saying that egress is the same interface. And now it's run the RASPF for the P4, but it's not the LFA router. And then it completes the LFA operation. So first it's run the LFA, then it's start with the Ti-LFA. So it has started the Ti-LFA operation, starting the operation for P2, but we don't have Ti-LFA enabled for the interface between P1 and P2. So it says that not configured for node P2. If we talk about the P4, this interface is also not enabled for Ti-LFA. So here it says that not configured for node P4. But this is the interface which we have configured the Ti-LFA. So it started the processing, Ti-LFA processing for link between PE3, PE1 and P3. This is that interface, and the required algorithm is linked. So by default it is link. So for node and SRLG we need to enable it. Then it's starting the Ti-LFA link protection for node P3. So how it calculates that it's removes this link, and then PE1 runs the SPF once again to find out the next best available, or we can say that post convergence path. And once it figure out that okay, post convergence path is via this node or this link, then it tries to calculate the P space and Q space for the P1 and P3. So you can see in this scenario, P1 and P4 both are in the P space, but PE5 not in the P space or not in the extended P space. P3 is not in the P space, not in the extended P space. Again, PE7 is the not in the P space and not in the extended P space. So based on that one, it has calculated that PE5 is the next Q node. So this has become P node and this has become Q node. So all these routers are part of the Q space of P3 or destination. Then based on that, routers are going to figure out the SID as I said earlier, for P node, router is going to use prefix-sid, and if you want to reach to Q node, it's going to use the adjacency-sid. So you can see here for P node, it is the explicit null, hence it is not showing any label here. But for Q node, it has figured out the adjacency-sid between P4 and PE5. So this is the case. P4 is become as a P node, where we are using the implicit null because it's directly connected to PE1. PE5 become the Q node, where we are using the adjacency-sid for that, and this is the SAP entry for that one. So if packet is living out of the backup path, it's going to have these many labels. First one is implicit for P4, second one is the adjacency-sid between P4 and PE5 allocated by P4, and then last one is the prefix-sid for the PE7. So these are the general steps. So first, router is going to run the SPF for all the prefix, that is using the rsvp for each neighbor. Once that is finished, router is going to start the Ti-LFA for the protected links. So it will see that which algorithm router needs to use, whether it is link, link and node, or link node SRLG. So it will bring down this particular link, it will remove this particular link, and then it's try to run the SPF. Once it find out the post convergence path, then he tries to figure out the PQ or PQ nodes. If LFA path is going via the post convergence path, it keeps the same. But if LFA path is not going via the post convergence path, sorry, here it should be post convergence, they need to replace with the Ti-LFA. What does it mean? Let's say from P1 to P7, LFA path is going via this way, but the post convergence path is this way. So Ti-LFA will replace this LFA path with the Ti-LFA. But let's say LFA path is going via the same path, and post convergence path is also going via the same path, and then Ti-LFA also has calculated the same path. So most of the time it keeps the loop free alternate path. So it has covered in the RFC 7490. Let's see how it calculates based on the diagram. So what is exactly the P space? If we talk the P space of the router 1, so it is this P space or the routers which router 1 can reach easily without going over the protected path. So if we calculate if we run the SPF, so let's say this is the SPF for the router 1, So in this scenario, this is the SPF graph for the router 1. If we remove this link, so router can only reach to the R5 and R4. So this has become the P space for the R1. Extended P space. So PLR router will see that to which routers his neighbor can reach without going over the protected path. So R5 can reach to the R3 without going via the protected path. So if we say that default matrix is 1, so let's say here 1 1 2, but if he wants to go via this path, then its matrix become 3. So R5 can reach to 3 easily, hence it's become the extended P space for the R1. So we can say that P space and extended P space is this one for the router 1. Q space. Q space will be always for the merger point or for the destination. So it is always same like what we discuss in the case of P space. It is the space for the router 2 where he can reach without going over the protected path. So router can reach to the 3 and 4 without going over the protected path. If we talk about the SPF tree or graph for router 2, this is router 1, this is router 2, this is router 5, and then this is 3 and this is 4. So if you remove this particular link which is protected, a router can have reach till R4. So this has become the Q space for her. So let's say this is the diagram and we are protecting the link between R1 and R3. So for R1, if we calculate the SPF, if we run the SPF, this is the SPF graph for the R1. And if we remove this particular link, so this has become the P space for the router R1. R2 and R4, these are in the P space of the router 1. If we talk about the Q space for the R3, if we run the SPF for R3, this is the SPF graph for it. And if we remove this particular link from here, then R3 can reach till R4. So this has become the Q space for R3. To find the PQ node, so this is the P space for the R1, this is the Q space for R3, and we can see that R4 is the common in the P space and Q space. So that node is become the so that node R4 is become the PQ space, PQ node. What is the extended P space? So it is on the behalf of the immediate neighbor where he can reach to the routers without going over the protected link. So in this case, R5 is become the extended P space for R1. So we can, if we talk about this one, this is the extended P space for the R1, and this is the Q space for R3. So in this case, P R5 and R4 become PQ node. Let's talk about more using this diagram. So if we talk about the p space of the R1, if we run the SVF, this is the SVF graph for the R1, and this is the p space for it. R4 and R5 are in the p space of R1. If we talk about the Q space, let's run the SPF for R2. So this is the SPF graph for R2, and this is the Q space for R2, which is R3, R6 and R5. You might be thinking, why not R4? But R4 has the ACMP path. You might be thinking, why not R4? But R4 has the ECMP path via this node and via this node. Means it can send the packet over the protected link or via this link. Hence it is not considered as a part of queue space. So R5 is become the PQ node here.